consciousness is an intellectual illusion.
The Earth and its oceans are a giant ventilator upon which all of our lives depend.
There's nothing right about giving a machine the right to kill people.
Good evening, everyone. Welcome to the 2021 16th Einstein Lecture. This year, the topic being space weather and the path to Mars. Tonight's event is presented by the New South Wales branch of the Australian Institute of Physics and UNSW Centre for Ideas, and supported by UNSW Science and Inspiring Australia as part of National Science Week. We have a number of excellent speakers who are international experts in the areas. These will be introduced later. I am Honourable Associate Professor Graham Melville. I teach and do astrophysics research at UNSW in the fabulous Dynamic School of Physics, where our research group studies the atmospheres of exoplanets and polarization of stars. I would now like to acknowledge the Bidjigal and Gadigal people who are traditional custodians of the land that UNSW Sydney is built. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are joining us today. This is an e-talk because of COVID, but at least we can enjoy the talk from the comfort of our homes, unlike what future astronauts will be up against in their Mars mission. Maybe someone in the audience may even volunteer, but there will be severe hardships. Not least of all being no cappuccino machine aboard the Mars vehicle. The Einstein Lecture Series is held every year in Science Week. Its goal is to use a prominent physicist, Einstein, to promote to the general public, especially young people, about the wonders of physics. In fact, the astronauts will be younger when they return to Earth because of their higher travel velocities, according to Einstein, by microseconds. The Australian Institute of Physics, or AIP, is Australia's premier physics organisation and promotes the role of physics in research, education and the community. The New South Wales branch is very active and has a number of activities throughout the year where we sponsor student events and competitions, as well as prizes, public talks like this one, and also visits to research organisations such as ANSTO and CSIRO. These are listed, but I'll just mention our next event is in October, Physics in the Pub, run by one of Australia's best science communicators, Dr. Phil Dooley. Unlike travelling at the moment, it is always a good time to join a great organisation like the AIP. See our website, aip.org.au. I would now like to welcome our chair for tonight's event, a renowned astrophysicist from UNSW School of Physics, Professor Sarah Brough. Professor Brough is currently leading Australia into a new astronomical survey of the southern sky. She has been a key member of 3 major Australian-led surveys of galaxies and evolution. And in 2020, she was the Associate Dean in Equity, Diversity and Inclusion at UNSW's Faculty of Science. Welcome, Sarah.
Thanks, Graham. It's lovely to be here, however remote we all are. And I'd like to extend a warm welcome to our audience tuning in tonight, including UNSW staff, students and alumni, along with the broad and diverse science community. As Graham said, I'm Sarah Brough and I'm a professor in UNSW Sydney's School of Physics. As Graham mentioned, my research focuses on galaxy evolution. My research community has a few potential CubeSat ideas for galaxy evolution research. But as well, I'm someone with a lifelong fascination about space, and I'm really excited to hear what tonight's speakers have to teach us about their research. Tonight, we are joined by Susanna Guatelli, Associate Professor at the University of Wollongong and an international expert of Monte Carlo radiation transport simulation codes for radiation physics, as well as Eva Cairns, Professor of Space Physics at the University of Sydney, who is a leader in Australia's space science community and director of QAVA, the training centre for CubeSats, UAVs and their applications. Tonight we'll be hearing from Professor Eva Cairns on space weather. Eva is a co-investigator on NASA's STEREO mission and since June 2019 on NASA's two new SMEX missions, Punch and Tracers. He led the Inspire-2 CubeSat project, which launched in May 2017 and re-entered, still working in November 2018. Inspire-2 and UNSW ECO were the first Australian-built and owned CubeSats to work in space and only the fourth and fifth such satellites. And now, over to Eva.
Thank you very much, Sarah, and thank you, Graham, and the New South Wales branch of the Australian Institute of Physics for inviting Susanna Guatelli and myself to give the 2021 Einstein Lecture. Space weather and the path to Mars perhaps doesn't remind people of Einstein because, of course, most of his famous works, or much of his famous works, were published in 1905, and the space age really only started in 1950. But I'll try and relate those current space efforts to Einstein. So space weather, as you've seen in the movie that you see in front of us, the sun is an active star, and most of the space weather that we see in our solar system is driven originally by the sun, and it propagates through the interplanetary medium, having been produced in the form of a coronal mass ejection like this, moving out at, let's say, 1,000 kilometers a second, or in a solar flare, and eventually interacts with the Earth and its magnetosphere. And you'll notice the magnetic field lines of the Earth. We'll talk about that a little bit more. And leads to effects that are of direct importance to humanity. As I'll argue in a moment, much of what we do in modern life depends upon space assets in particular. Think of yourselves without GPS, without the radio, without electricity. It would be a rather different life that we led or lead. And all of that is partly at least dependent upon space weather. Of course, the Earth is not the only relevant part. The events coming from the sun also go past the Earth and can interact with Mars, and that's then relevant to astronauts as they move toward, or cosmonauts as they move towards Mars. And that's in particular the part that Susanna will talk to you about. So my part really is about space weather itself and why we should care. And I'll start with an overview of what space weather is, then talk about a process called magnetic reconnection, which leads to flares and X-rays. And this is where we'll start to see the connection to Einstein. Then talk about coronal mass ejections and energetic particles, which again is what Susanna's really going to be focused on. I'll bring in the Inspire-2 CubeSat and the damage that it experienced due to space weather. As Sarah mentioned, CubeSats are really important in my current research. Then talk a little bit about the QAVA-1 CubeSat, then lead into the electricity grid and associated disruptions, and then it'll be short conclusions and over to Susanna. So space weather, basically these are the conditions in space that may affect human systems and activities, whether on the Earth or in space. Almost all of them are driven by solar activity, and the events can be really small, almost not noticeable, to ones that can knock or could knock human society back to the Stone Age. So-called Carrington event in 1859 is one such event, which luckily for us is pre-electricity grid and pre-space age. And we'll talk, though, a little bit about an event in 2012 that missed Earth by 90 degrees. It went off 90 degrees to the Earth-Sun line, and so we didn't experience it. And yet we here on Earth need to be able to predict and mitigate especially large space weather events. So let's talk a little bit more about the big picture. We'll be looking at events coming from the sun. Here we have a coronagraph with the black disk obscuring the sun, which is the white disk in the middle. We see a snapshot showing a coronal mass ejection with a mass which is a good fraction of an Earth mass, moving out at about 1,000 kilometers a second. And it's bright because it's reasonably warm, and it's also dense. So it scatters the thermal radiation from the sun to us. This moves out through solar wind, interacts with the Earth and its magnetosphere. You'll notice the magnetic field lines of Earth, nice dipole here. And we're looking at influences inside the magnetosphere that affect spacecraft, for instance, and then the ionosphere and the ground. Now, we could make this talk really quite complicated. Here you see some of the regions of the magnetosphere leading down into the ionosphere, and I'll just talk about two. One is the cusp region, which you can see by its shape is funneling plasma from the solar wind. Plasma is just an ionized gas. So plasma down towards the poles of the Earth and giving us the aurora. I'll also mention the radiation belts or ring current here, energetic particles bouncing back and forth in Earth's magnetic field and drifting around the Earth. And those are very relevant for the radiation effects that are important. This video is going to show qualitatively how space weather at Earth develops. What we'll see is a sudden burst of radiation in a solar flare, and a large amount of material will become visible off to one side of the sun on the right-hand side. It will then start to move towards the Earth, which will come in view, and you'll see the magnetic field lines of Earth. Eventually, when the coronal mass ejection gets to Earth, we see changes in the magnetic field lines. This is a so-called magnetic reconnection. And this occurs both at the front side of the Earth and also in the back side in the magnetotail. And then we're going to see energetic particles moving down into the auroral zone and giving us the well-known aurora. And this is the basic picture. Coronal mass ejections cause magnetic reconnection. They heat and accelerate plasma, give us energetic particles, heated plasma, and space weather events. So here are some of the zoo of space weather events that we're going to look at. And we're going to start off with those involved in the safety of astronauts and humans. So to do with galactic cosmic rays, which are a background that Susanna will mention more, and just the energetic particles coming from the sun. Those can give humans radiation damage. They can also affect computers and computer memory, giving so-called single event upsets. They can also damage solar cells, charge spacecraft. A lot of damage to spacecraft can result. What else can those energetic particles do? Well, they can heat up the atmosphere together with X-rays, which come from the sun, and cause excess ionization and heating in the atmosphere. The atmosphere can then puff out, giving us increased drag for satellites, for instance, causing them to re-enter. We also have changes in the magnetic field due to that magnetic reconnection that I mentioned. A time-varying magnetic field gives rise to an electric field, and thereby currents, for instance, in the ionosphere. Those currents will themselves have magnetic fields in them, and the time variations give rise to electric fields or voltages along electrical power lines, causing large currents to flow there and sometimes destroy the transformers. Same sort of problem on pipelines. What else can the motion of plasma and the currents give rise to? They can give rise to so-called plasma bubbles that scatter the radio waves moving through the medium. So it might be your television reception or your radio reception, or it might be the GPS signals that you rely upon. So many effects due to space weather that we'll be discussing a bit more now. Now, why is it important? I mentioned the Carrington event of 1859, now considered to be about a 1 in 100 year event that gave rise to the aurora. Instead of being up in Norway and parts to the north, 60 degrees magnetic latitude and higher, moved all the way down to 23 degrees. In fact, even being visible from Hawaii for a while. Gave rise to all sorts of issues with these magnetic field, time-varying magnetic fields and currents, indeed arcing from telegraph wires. And it's predicted that if that event occurred today, it would have taken out the American East Coast power grid, destroying the transformers for about 10 years. So looking at costs of order $1 trillion a year. And for reference, the Iraq War cost about $1 trillion. It's not just rare, very rare events. In 2012, we missed a Carrington-style event by 1 week, as I mentioned. What about a smaller one? 13th of March 1989, Quebec event, probably about a 1 in 30-year event. Took down the electricity grid in Quebec, about 90 seconds, leaving 6 million people without power for over a week. Damage around the world, and we're looking at economic costs directly from the electricity not being sold of $2 billion, total economic damage of order 13 billion. So huge costs, and even small events give rise to costs of order of $100 million a year. And yet our space assets and our electricity grid are increasingly important for our modern life. Try to imagine life without them. So really, space weather is really important to understand. Here are just some examples, standard Earth observations, important for these particular reasons here. Huge amount of applications. Same sort of thing with GPS and GNSS. For instance, almost all global financial transactions are timestamped with GPS. If you lose the GPS, you lose the financial services. Stock market grinds to a halt, for instance. And what about using it for position navigation and timing, aircraft landing, cars, etc.? We really need to know when our space assets are going to be affected, and things like GPS are not available for us. And for that, we need to understand space weather, magnetic reconnection and flares. And in some sense, the idea is rather simple. You see on the left, you see some magnetic field lines which are anti-parallel, being brought in together by a plasma flow. And this is a bit like eating a burger or a large sandwich. As you bring it towards your mouth and you start biting, what usually happens? Unfortunately, a lot of the fillings usually squeeze out to the side. And that's what happens here. Plasma's coming in here and here. It's got to go somewhere. We have to conserve mass after all, so it gets squeezed off to the side. And as it does so, it carries a changed magnetic field. Notice that the magnetic fields here are in the horizontal direction primarily, and here on the sides in the outflow, they're primarily in the transverse direction. So you're changing the magnetic field topology. But you're also doing more. If you move these magnetic field lines, which are of equal magnitude in this picture, towards the center, and you superpose them, the resultant field is 0, and yet the magnetic field energy goes as the magnetic field energy squared. So it's 0 in the center, was non-zero here. Where does it go? Got to go somewhere. It goes into outflow and heating. And so what we might expect in regions like this for a solar flare, we've got a nice magnetic field loop here being stretched out, anti-parallel field lines here, they get brought together. You can naturally have plasma flowing down here and out. The plasma that goes down here is going to give us X-rays and heating of the lower portions of the corona, and the parts that go out like this are going to give us coronal mass ejections. So let's have a look at that. Here are some examples from some recent work. What we should see is outflows here, moving very nicely out. All of these magnetic field loops here, lots of changes with time. And here again, we see these outflows, jets of material, hot plasma moving out as a result of magnetic reconnection. And what we're seeing here is a proxy for the magnetic field reconnection. This is ultraviolet light. You see these nice events. And then occasionally you see a nice little radio event here. That's the blue. And the red here is the X-rays that are produced. And we're going to talk more about those X-rays. But this is an example of magnetic reconnection giving rise to X-rays and so-called type 3 solar radio bursts. Here's another example. What we see are magnetic field lines evolving. We see red was X-rays. Blue, we'll see gamma rays in a moment. And you'll notice this snow of dots being produced every so often. Those dots are the energetic particles hitting the detector frame. Similarly, if they were hitting your eyes, they'd be irradiating them. Here, luckily, it's just irradiating the detector plate. You'll notice again, it's hot here because it's bright, and that's where the reconnection's been occurring, for instance. So again, another example of magnetic reconnection, X-rays, and heating. So let's go to the connection now to Einstein. You perhaps will have all heard of the photoelectric effect. So what does that involve? Well, here's an example where you've got some electrons floating freely in a metal with the ions in a regular grid. Incident light of the right frequency was observed to show electrons being emitted. But it didn't happen for any light, and it didn't, as in wavelength of light, had to be a short enough wavelength or high enough frequency, in other words, blue or purple rather than red, for instance, and it didn't matter what the intensity was. Here's just an example of this, where someone's going to be getting some electrons onto a metal plate, putting them onto an electroscope here. You can see the two wings separating due to the electrons repulsing each other. You then put an ultraviolet light over the top, and you push the electrons off the plate at the top, and gives rise to lower charging. Here it is again. You can see the shadow here of the electroplate. And then let's just go ahead. If you put a device in front of it to stop the ultraviolet light hitting it, you still see it there. Now you don't. So how is that explained? This is Einstein's work in 1905 that he got the Nobel Prize for. The idea was that light's acting as a particle, a photon here, with an energy given by h times f. And the electron absorbs a photon, gets enough energy to get out of the metal, and it takes a certain non-zero amount of energy to leave that metal. And it's just energy conservation. So a photoelectric effect. So if some of you will have heard of Feynman diagrams, here's a Feynman diagram, time going this way, electron absorbs a photon, and it becomes a higher energy electron. That's the ordinary photoelectric effect. But can it go the other way? Can time be reversed? In other words, can you get a high energy electron giving you another electron and a photon? And so that is Einstein's 1911 idea of explaining Bremsstrahlung, where you had some electrons leaving a cathode being accelerated by a high voltage to a target, and then you got X-rays. Here's the spectrum of X-rays. We'll talk about them later perhaps. And here's the minimum wavelength or maximum frequency for the X-rays. And Einstein explained that in terms of that being the case where all of the energy of the electron goes into a photon. So that's one connection to Einstein. So here we have another example of a coronal mass ejection moving outwards, the energetic particles that we see giving us this snow. Here's another just snapshot showing the coronal mass ejection like this. I won't talk about how the shocks in front of these coronal mass ejection accelerate particles, but I could do so if I'm asked questions. So how does this relate again to Einstein? Well, most of you will have heard of Brownian motion, where individual particles move around in a microscope. You can see blobs of material moving around. And he explained that in 1905 as evidence for atoms using a kinetic theory. Cloud chambers a little bit similar. Here you have a chamber, which we hopefully see in a video here, where you've got flowing air supersaturated with water, and then you have some energetic particles going into that. They ionize the gas molecules, which then act as condensation centers, and you get this track of droplets. So let me just go over this. Here's a cloud chamber. Here's, for instance, the tracks leaving a radioactive source, alpha particles moving out. Here's another one superposed of an electron moving. And you see it, the idea that the fatness of the trails relate to the amount of energy being deposited. And so the alpha particles here, which are just helium nuclei, have more energy that they deposit. And that's important for Susanna's work, for instance. So a cloud chamber, beautiful piece of classical physics. What about modern times? Well, here's the various quantities for solar cells on satellites. You'll see here at August of 72, large changes in the voltages, the currents, the power from the solar cell as a result of radiation damage from these energetic particles coming along, knocking holes basically in the current channels and stopping the solar cell from being able to produce significant power. So I promised that we talk a little bit about CubeSats. So what's a CubeSat? It's basically one cube of a CubeSat is a 10 centimeter on a side cube. So 1 unit here. This guy here is Inspire 2. University of Sydney, UNSW, ANU collaboration that we flew in space. And as you heard from Sarah, it's the first Australian CubeSat to work in space and only the 4th Australian-built satellite to work in space. We demonstrated many things with Inspire. One was breaking the economic and technical barriers to us Australians entering the modern space age, but we also managed to do a little bit of space weather science. Of course, I have to show you the mandatory pictures of the launch, which I could talk about. And then here we'll talk a little bit about space weather. And so here in this panel here, we see the flux of energetic protons. See nothing for a long time, then a sudden event, another smaller event, and then some other big events. Time on the bottom here, you've got month scale. These are the time-varying magnetic fields that we'll talk about next. And what we have here is the current from the solar cells of Inspire 2 varying as it goes from daylight to night during local eclipse. And you'll see that we have life here. And then right at the end of this smaller space weather event, the spacecraft goes dead. Goes dead for about 1.5 months. We were able to resuscitate it and get it working again nicely despite another large energetic particle events. And then after the event, it's at 0 temperature. Our next satellite is a 3-unit CubeSat, Kuiper-1. It's ready for launch. It should get launched at the end of this month on the 29th of August. And here, for instance, are our colleagues in Japan from Space BD and JAXA accepting the spacecraft. I mentioned time-varying magnetic currents. What we see here is a little experiment where you're going to look at time-varying magnetic currents and just putting a magnetic field, a coil into a magnet into a coil, and you see the changes. And it's the same sort of thing here on Earth. Here are the currents obtained on various power lines. You see things up to 30 amps, 16 amps, huge currents going through a transformer that might be going at 100,000 volts. So huge amounts of energy being put into the system. You can easily destroy them and be very important quantitatively. So let me just say a little bit more about space weather and why we need protection. Basic idea is that we, or at least our modern society, depends intrinsically on space and associated assets. And to mitigate the effects of space weather, we need to be able to predict them accurately. And yet at the moment, we can't. I showed you some solar flares. We can't predict when they'll occur. We can't predict how intense the X-rays will be. We can't predict the amount of satellite drag in the ionosphere and atmosphere. We can't even predict accurately enough. At the moment, it's 10 hours plus or minus 1 error for a coronal mass ejection hitting the Earth. Some pilot work that I and others have done gives about 2 hours error, much better, but still not good enough. GPS dropouts, electricity grid, energetic particles, all of these things are vital to be able to predict, especially if we're wanting to predict, or if we're wanting to have people go back to the moon and go to Mars. We need to make sure that our astronauts are not going to be irradiated, and if they are, that they have time to get to somewhere safe. Are, of course, major efforts worldwide, and a group of us is banding together to propose a Centre of Excellence called Aspire to address these questions. So, enough from me. These conclusions: space weather, its effect on human systems and activities on Earth and in space due to solar activity. Economic aspects are absolutely important, and so are the effects on everything electrical that we work with in our life. CubeSats are really important too. For instance, ionospheric space weather, and using CubeSats to look at the varying changes in the ionosphere. It's one place we can do really global leading work, and we need as a society to understand better and be able to predict space weather. And we here in Australia need to play our part. So without further ado, energetic particles and radiation from space weather. On to Susanna now as she takes us to Mars. Thank you.
Thanks, Eva. It was fascinating to hear about the economic cost of space weather and how that can be, the space weather is explained by the use of those kind of really fundamental physics, and to see that real need, that kind of desperate need for better predictions. And I can see how useful our physics students will be at both universities going forwards. 3 universities, lots of keen physics students available. So we'll now hear from Susanna Guatelli on the impacts of radiation on the path to Mars, so looking even further away. Associate Professor Susanna Guatelli is an international expert of Monte Carlo radiation transport simulation codes for radiation physics. These include medical applications, as well as radiation protection in Earth labs, aviation, and space. Her PhD focused on radiation protection of astronauts in missions to Mars within the Aurora project of the European Space Agency. Based at CERN in Switzerland, she contributed to projects spanning radiation monitoring for the Large Hadron Collider, to the effect of radiation at DNA level in astronauts. Associate Professor Guatelli is passionate about science communication and inspiring young people to study physics. And now over to Susanna.
Thank you, Sarah, for your very kind introduction. And thank you again to Graham for inviting me in this event. A human mission to Mars has been identified as one of the next main goals of human exploration of the solar system. This has been defined in the Global Exploration Roadmap, which has been drafted in the past years, in 2018, by 14 space agencies. A human mission to Mars is envisaged for the next decade, and it is anticipated by a human mission to the moon. The human journey to Mars would consist of at least a 2 years mission. We have 7 months for the astronauts to reach the red planet, and then 7 months to come back. The astronauts have to stay at least 3 months on the Martian surface to do experiments. So the shorter mission to Mars would be about 2 years, but there are designs of these missions that span also for more time, like 3 years. Unfortunately, a mission of astronaut to Mars poses severe risks to the health. There are physiological problems caused by reduced gravity. In this condition, our bones become brittle and our muscles become weak. And psychological problems caused by isolation. And finally, there are acute and later risks caused by exposure to cosmic radiation. And this is the topic of my talk today. As Ivor said before, there are solar particle events which are emitted by the sun. They are mainly protons, and they can cause acute radiation effects from nausea and vomit down to, in severe cases, to death. The problem of solar particle events is that they are unpredictable. And then we have a background of radiation that permeates the space. These backgrounds are galactic cosmic rays. They are 75% protons, 24, let's say, percent of helium nuclei, and then 1% all the other elements. Galactic cosmic rays are more intense during solar minima because during solar maximum activity, the galactic cosmic rays are scattered away more efficiently by the solar winds. Galactic cosmic rays can produce chronic effects, like they increase the risk of cancer, disease to the central nervous and cardiovascular systems. On Earth, we are shielded by the harsh radiation environment by our global magnetic fields. But in a mission to Mars, on Mars, there is no such a global magnetic field. So astronauts on the surface of the red planet would be exposed to the harsh cosmic radiation environments. And in addition, when galactic cosmic rays and when in general cosmic radiation is incident on the surface of the red planet, can have nuclear interactions and produce a secondary radiation field. And this also can pose an health hazard to the astronauts. How do we study the effects of cosmic radiation in the astronauts? Well, we look at the early mechanism of damage in the DNA. This slide wants to summarize in a nutshell the early mechanism of radiation damage. So radiation can interact directly with the DNA strand, deposit energy, and break the DNA strand. Or the radiation can have physico-chemical interactions with the water molecules, produce free radicals, which also can break the strand. The more strand breaks we have, the more difficult it is to repair this damage. So the more radiation we are exposed to, the more the cell can mutate and eventually die. There has been a very interesting experiments done by NASA that demonstrates the core of the problem of radiation exposure in space. These experiments counted the double strand breaks in the DNA. So they counted when the DNA was broken by the action of the radiation. They've done these experiments irradiating mammalian cells with gamma rays. And the double strand breaks have been dyed, and you can see them here in this picture represented. They correspond to the gray dots. And you can say that the double strand breaks are sparse in the nucleus of the cell. But then if we look instead, if we irradiate the same nuclei, but with the silicon or iron nuclei that we find in the cosmic radiation, we can notice that the double strand breaks are more clustered. And this damage is a lot more difficult to repair. And this is because the track structure, what we say in physics, is that the track structure of the particles that we find in space is a lot more dense than the typical radiation that we can find on Earth. We have an understanding of the biological effects of radiation in the terrestrial environments. But when we talk about the biological effects of cosmic radiation, well, our knowledge is poor. And there is a lot of research in this context. In a nutshell, provided our knowledge of the space radiation environment and of its effects in the biological medium, the excess lifetime risk of cancer death due to exposure to space radiation is estimated to be between 2 and 20% for a human mission to Mars. Well, unfortunately, the astronauts' limit is only 3%. So we accept, what is accepted is that 3 astronauts in 100 can die because of cancer produced to the exposure to cosmic radiation. So we can say that the human mission to Mars poses problems for the astronauts. But what do we do? Do we send astronauts in space and we look at what happens to them and maybe they get the superpowers like the Fantastic Four? Well, this is not what we do, but we have to do research to improve our knowledge of the space radiation environment and of its interactions with matter, to understand better the biological damage of cosmic radiation in human tissues, to develop radiation monitoring systems and shielding solutions for the human mission to Mars. We needed to have an instrument to be able to predict the radiation doses in the astronauts. How do we do this? Well, on Earth, we have some accelerator facilities like the one depicted here, the NASA Space Radiation Lab or the Brookhaven National Lab, where where the cosmic radiation environment can only be partially reproduced. So this is a facility, these kind of facilities are extensively used for space mission research. And then we have experiments on the International Space Station, and also beyond that, we have like robotic missions on the Moon and Mars that can also provide the insight on those levels. To have experiments in space is very very good, but these experiments are sparse, the results are difficult to reproduce, and they are very expensive. So what we can do? Well, in physics, we have radiation physics simulation software tools that describe particle interactions with matter, and they allow to solve in a very cheap manner, let's say, theoretical problems that support the space emissions and that work in synergy with the experimental measurements done in Earth lab facilities or in space. One of these Monte Carlo simulation tools is called JAM4, which is developed since the 98 by an international scientific collaboration based at CERN, and I'm part of this collaboration since 2002. And my work since when I was a technical student at CERN was to contribute to extend the JAM4 from high energy physics problems to medical physics and space science applications. And nowadays, I'm leading an effort called the G4Med, which includes about 50 researchers to improve this software for medical applications, including radiation protection. Well, on the right, you can see an example of a simulation. We have the blue tracks represent an helium nuclei beam that is incident on the cell, and we can study the energy deposition in the cell, the number of double strand breaks produced, and so on. These physics simulations can be used to solve many different problems. And today I would like to show to you some simulation results that we got at the Center for Medical Radiation Physics of the University of Wollongong in the context of radiation protection of astronauts in long-term missions to Mars. Well, we model in JAM4 as a first step the Columbus module of the International Space Station, which is represented by this tube. It's open-ended just for visualization purposes. And then we model the radiation field, which in this case the radiation field is 10 galactic cosmic ray protons and are represented by these green tracks. And then we can model more galactic cosmic rays incidents on the Columbus module. And you can see that we have a lot of tracks in this case. Well, what happens is that the galactic cosmic rays, when it interacts with the structure, in this case of the Columbus module, produce a secondary radiation field. But let's see this in more detail. So here we have a galactic cosmic ray proton that goes through the Columbus module of the International Space Station. So, which is represented by this white line. The incident galactic cosmic ray proton can have nuclear interactions and produces these secondary radiation fields. So we can see yellow tracks that represent gamma rays. We can have secondary neutrons, which also pose a risk to astronauts' health. And then we can have other particles. We have heavy nuclei, like a helium nuclei, aluminum nuclei, and other nuclei species. So it's important for space to find suitable shielding material that allow on one side to shield from the cosmic radiation, but on the other side also to limit the generation of this secondary radiation field. Well, it has been found that materials are a very efficient shielding solution. Because they limit the origin of this secondary radiation field. But what is a nitrogen-rich material? Well, polyethylene, which you find in your water plastic bottles and in your grocery bags, has been identified as a suitable material. And therefore, these sort of materials, like polyethylene, are used for the so-called passive shielding. So we can use this material to shield the astronauts in transfer vehicles. And then what we've done in the simulations is to model anthropomorphic phantoms, which represents the astronauts, and we calculate the dose due to radiation in different organs. The simulations take a very long execution times, and therefore we use the National Computing Infrastructure in Canberra to run our simulations. We calculate the doses. The dose in physics is defined as the ratio of the energy deposited by the radiation divided by the mass of the specific organ that we are interested in. And then what we do, we compare to experimental measurements, because whenever we have a simulation, then we have to quantify how accurate are the results deriving from them. So in this case, we had a good agreement. We compared them. We had a good agreement with experimental measurements that measured the dose in an anthropomorphic phantom represented in this picture called Matryoshka. The dose in astronauts must be determined in organs at risk, like the brain, the heart, the skin. The skin is for burns, the eyes because of the risk of cataract, in the reproductive system because of possible risk to the progeny, in the bone marrow because of the associated risk to develop leukemia. And once that we define that we know which is the moments we know which is the predictive power of our simulation tool, then we can predict the doses in other space emission scenarios. Keep always in mind that when we predict doses, because of the large uncertainties that there are, let's say that the error bars are pretty large. So here I show to you some results for an astronaut that has been set on the lunar surface. We calculate the daily absorbed organ doses on the moon surface, and also in this case we compare to existing experimental measurements, and we can say that we are in the same order of magnitude. Now we are using these simulations to study various shielding solution of astronauts on the moon and on Mars. So in general, so simulation studies that have been done in the scientific community show that the dose due to galactic cosmic rays may be about 100 times the case of pilots of commercial flights for 1 year, which is also, to give you an order of idea, 300 times the annual limit of general public. So, and this corresponds, just to give you an idea, to about 900 chest X-rays. So, in order to limit the exposure to radiation for astronauts on the moon, but also on Mars, the idea is to build the shelters of astronauts in lava tubes, which are natural tunnels that we find both on our natural satellites and on the red planet. But then we can use Jump4 simulations to study passive shielding solutions in transfer vehicles to Mars. And here I like to show to you an example of study that I've done within the REM-SIM project with Alenia Spazio, INFN, and ESA. So I had to model in the simulation this concept of a transfer vehicle, which consists of an inflatable balloon of hydrogen-rich materials. And then there is a solar particle event shelter in the center, which is surrounded by a rigid water equivalent wall. Where here the astronauts should recover in the case of a solar particle event. Well, I ran the simulations and I found out that the 75 centimeter thick wall protecting the solar particle event shelter can shield fully the astronauts, or let's say almost fully the astronauts from the solar particle events. Unfortunately, passive shielding solutions are not adequate for cosmic radiation, for galactic cosmic rays, for galactic cosmic rays. This happens because galactic cosmic rays are a lot more energetic than solar particle events, and therefore it's a lot more difficult to shield them. So one solution that is under study is to adopt active shielding solutions. Here on the left, you can see a sketch by NASA where the transfer vehicle is surrounded by superconducting coils, and the idea is to generate an intense magnetic field surrounding the transfer vehicle, and that will protect, that will shield the transfer vehicle from the incident cosmic radiation. Here on the right, I show some results obtained by means of Jump4 by Ferrone and Cry of the University of Texas, where they did a study about which must be the intensity of the magnetic field in order to limit the hazards of radiation to astronauts. And it has been found out that active shielding solution can be a viable strategy. Well, towards a mission to Mars, a mission to Mars would be about 2-3 years. Simulations, Monte Carlo simulations, and coupled with existing experimental measurements showed that 3 years mission would correspond to about the astronauts' career limits of the European Space Agency. In the case of NASA, the career limits depend on gender and age. And and for NASA, for example, female astronauts with an age that is below 40 years old would have big problems to go to Mars with the current career limits because of the exposure to cosmic radiation. And actually, you may have read that actually NASA is considering to revise the radiation limits, the career radiation limits for astronauts in order to increase the diversity in the astronauts corps. Again, to give you an idea, 3 years mission would correspond to about 400 times the annual limit of pilots of commercial flights on the Earth, and corresponds to about 1,200, 1,500 times the annual limit for general public on the Earth. So in summary, the cosmic radiation environment is harsh, beyond our let's say global Earth magnetic fields, and radiation physics simulations are important to support the human space missions, and they work in full synergy with experimental measurements. Thank you very much.
Thanks, Susanna. That was fascinating to hear about the radiation effects on astronauts in space and the modeling of the radiation environment in that region. And as well, thank you, Eva, for such interesting talks. Now we're going to dive into a conversation, and we've got some great questions here from our audience, which I will dive into. So I wanted to start with one. We've got the Martian on the screen right now, and this is a funny one because I'm often asked this myself. What do you think about the science shown in the Martian, i.e. the botany on Mars, the water oxygen reclamation methods? What do you think?
Yes. So what I would like to answer for what concerns my field of research. Well, the Martian is in this lab, which is on the surface of Mars. Well, I think that for a long-term mission, that is not a great solution, because the astronaut could really be exposed to galactic cosmic rays that actually will produce chronic effects, and solar particle events could also severely affect the health of the astronaut. The idea also for Mars is to build shelters which are in lava tubes. In lava tubes. And secondly, I'm not sure if it's a good idea to cultivate potatoes in the Martian soil. I mean, it's very rusty. I'm not sure. Maybe it's a little bit toxic.
A very high iron-rich diet.
Yes. Yes, there are, yes, for the diets, one, I know that there is a research that studies into sources of proteins, and one idea is to use, to have a diet that include insects that may help the astronauts in long-term missions.
I was going to ask Eva, so we've got a question from Elord Justo. What roles can cube satellites play in manned space exploration?
Well, that's a very open-ended question. So obviously CubeSats and satellites in general are very good for things where you want something robotic. So you don't need the people. You want to so that could be because you don't want to spare the resources to keep the humans alive, and it could be because you're interested in the fundamental plasma physics or some other aspect. So what are you going to? So I guess. So usually, if you're going to combine CubeSats with a human mission, you're going to want the CubeSat to do something the humans can't. And probably one way to look at that is perhaps you want more spatial information, as in the humans presumably in a spacecraft, and that's only one location that you're sampling the galactic cosmic rays, or the the thermal plasma, or the magnetic fields. So if you want to get more of a 3D picture of what's going on, the energy flows, the motion of energetic particles or plasma from one place to another, you might want to have your human vehicle in the middle and an array of CubeSats around it, so as to be able to focus or be able to view it in 3D. But in general, probably you're going to want to focus on things that the humans aren't going to want to do, whether that's putting antennas, for instance, on the surface of the moon and leaving them there, and then looking at the radio signals coming from the sun or the galaxy as a whole. That would be one thing you could do, but you don't have to do it on the surface of the moon. You can do it in space as well. So I think you can do many different things with CubeSats in conjunction with human missions. And there I was mentioning scientific aspects, but what about other things like creating a GPS system around the moon, for instance? That's a very natural use for CubeSats. Same sort of thing for radio communications. As you know, our Chinese colleagues have a satellite relay that's bringing their signals from the backside of the moon to the Earth. And there they're using, okay, it's a little bit bigger than most people's CubeSats, but it's a satellite. So communications is one thing. Sorry, I'm getting a mental blank on the other thing I just mentioned. Communications, GPS. I think there are many different aspects.
Yeah, I think that's a really great perspective on where they would be really useful. Lincoln Pangfilio asks, the now defunct Mars One plans to create a layer of protection by insulating a spacecraft with water, which can also be used for drinking. Is that a viable possibility?
Yeah, yes, the fact is that different materials, they are under study. There is polyethylene, as I mentioned before. Yes, I saw designs to have the walls that are filled with liquid water. There is a lot of study on new materials, actually. So hydrogen-rich materials that have boron inside, because boron absorbs better neutrons. So there is a very active research field in this domain to find the best materials for passive shielding.
Yeah, is weight an element of that? Because when I think about water, it's such a heavy element to be carrying into space.
Yeah, this is thank you. This is a very important point. We have always to pay attention, let's say, to the weight of the material that we send into space, because it's associated with the cost. So there are actually, that's why we do simulation studies, is also to optimize the shielding thickness, because for galactic cosmic rays, for example, which are a lot more energetic than solar particle events, even if I put 75, or if I put 1 meter thick polyethylene or water equivalent wall, well, that will just stop a couple of % of galactic cosmic rays. So actually, we increase a lot the weights of the material that we have to send to space, but at the end we don't get a big gain in terms of radiation protection. So yes, so absolutely there is a compromise. There must be a compromise between weight and efficiency in protecting the astronauts. from the radiation.
And since SpaceX's Starship is intended to make its first crewed flight to Mars in around 2026, are we on track? I was going to ask, are we on track to mitigate radiation using those, the current or kind of those near future technologies, or are we still quite a long way away?
This is a very big question. My personal, my personal opinion is that to have a mission to Mars in a few years, in 3, 4, 5 years, is a little bit premature, but I'm sure that the SpaceX, the staff, they are aware of all the risks the astronauts may have in a long-term mission. So I don't know which is their business case or their plan, but I find it a little bit difficult to send astronauts to Mars in few years' time.
That's certainly the opinion of various of my colleagues in the United States, that it's very premature.
And that's why, thank you, Ivero. That's why I think it's a very important instead to proceed to a human mission to the moon. That instead is a lot more feasible, and a human mission to the moon, maybe a little bit, a human mission to the moon, and to create a lunar base of astronauts, a permanent lunar base of astronauts, which is also one of the goals of space research, that will be very useful to solve problems that then will be encountered in longer term missions towards Mars.
Mm-hmm.
Yeah, I think that's a really important point. Eva, I think this question would be a good one for you. Can the usage of cosmic rays as propulsion bear any fruit compared to conventional propulsion techniques?
Right. So in some sense, that's just a variant of a standard rocket motor. As we're all aware, a rocket motor, you're going to have some energy deposition and some fast particles move out the back in one direction, and by conservation of momentum, your spacecraft goes the other direction. And I think what your question is wondering about is, well, can we just have cosmic rays or cosmic ray-like particles as the reaction medium that comes out the back? And so the answer is yes, in principle, but you have to accelerate the particles up to cosmic ray energies and direct them in a suitable direction, and that's really hard. I mean, in space, cosmic rays are believed, well, there are various theories for where cosmic rays come from, but one of them is that they come from supernova shockwaves. So rather like the coronal mass ejections, which have their shock waves in front of them, you can have a supernova shockwave as well, and the particles basically get bounced back and forth across the shock wave in so-called diffusive shock acceleration. But the point is, you need to have large distances. You need to be able to go back and forth across a shock wave, which might have, at least in nature, you're looking at distances which are hundreds of kilometers, if not, millions of kilometers back and forth as they get scattered. And we'd be having to do that same sort of thing in a human spacecraft. So I think really, unless we came up with a very clever way to produce energetic particles going, at the speed of light, which is the cosmic rays, I don't think it's very practical. And at the moment, there's no way that I know of to do that.
I'm also curious. So Mehak Preet Kaur asks, how do you think Australia will pave our way into space exploration?
Well, space exploration doesn't actually have to be very expensive. The Inspire 2 CubeSat, for instance, cost less than 200,000 Australian dollars in money that we actually had to pay. And yes, if you include the cost of salaries and so on, it's a couple of $1 million. The CubeSat Koala 1, which should get launched in roughly 20 days, it's the cost for the components and so on is, and the launch and so on, is closer to $1 million. But $1 million is not a lot of money. $1 million is approximately the cost for a Boost Juice franchise, for instance. So for a small cafe, for instance, that's the sort of amount of money you're looking at, $1 million or so. So that's very inexpensive. And it's interesting to note that NASA spends, or approximately, the NASA budget is of order, depending on how you count it, of order 20, let's just call it 20 billion American dollars. So about, 30 billion Australian dollars. Our current space agency gets about 0.1% per capita of that, 0.1% per capita. So, less than $100 million a year. It's closer to about 30 million or so. And yet $30 million is trivial compared with the budget of Australia as a whole. So I think my answer is that space exploration doesn't have to be expensive. Certainly not if you're doing it using robotic means. If you're going to involve humans, and you're going to go alone, then the price becomes large, no question. But if you share, like, if we shared with the European Union, or we shared with the Americans, or we shared with others, China, for instance, or Russia, the costs can come way down because we can basically use their infrastructure and do things that add value. So personally, I don't think there's a financial problem with Australia investing significantly in space and having a world-leading space program in certain parts of space research. Yes, we can't do everything. We're only, 25 million people, but we can choose a number of, substantial areas to be in, and we can be world-class for, amounts of money which are, perhaps twice as much as we spend at the moment. And that's a very reasonable amount of money, because we're looking at trying to develop Australia's space industry. Governments all over that at the moment, not perhaps funding it as well as they should.
Yeah, it's a really positive ecosystem kind of forming right now. It's a really exciting time for space in Australia. Now, I've just got one final quick question, and then we'll kind of wrap up. And that question was just, who can, should, and will claim Mars or part of Mars as theirs, in your opinions?
I'll let Susanna answer that first.
I'll let Ivor answer to that first. I don't know. I don't know.
Well, okay, well, I'll answer then. Based on the United Nations Copuous Treaty, it is not possible for any signing member or signator of that to claim possession of an object in space. So it would not be possible for at least a signator to claim Mars as theirs. They could claim a bit of Mars in the sense that they would be able to go there, live there, develop their whatever facility that they're wanting to do there, mine it, live there, etc. That would be perfectly fine, but they wouldn't, according to the treaty, be able to claim it. And that's true for the United States, which is a signator. It's true for Australia. It's true for most of the big countries. And personally, I think that's a much more sensible way to go, rather than, allowing the equivalent of, the exploration of the Earth, where people who would arrive there would, plant their flag and say, this is mine. I think we should go for the global commons approach and a United Nations approach and not own things like Mars.
Yeah, and I'm very hopeful that we do manage to achieve that going forwards. Susanna, do you have a quick thought?
Yes, this is, I would like that it will really be like that, because I don't know, maybe who knows if anyone one day will change these agreements. I think it's a very important question. It's a very important question. I hope. Sorry. I hope that the states and the nations will respect these agreements, and that this agreement will not be changed.
I think we'll leave it on that positive, hopeful note. And I'd like to say thank you very much to our audience for tuning in to Space, Weather and the Path to Mars. I'd like to thank our speakers, Susanna and Eva, for their time tonight, and our audience for joining us. To hear more of events, including UNSW's large National Science Week program, please subscribe to the UNSW Centre for Ideas newsletter. And that is us done for today. Thank you.
Thank you.
Thank you. Thank you very much.